Welcome to lecture number 47 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done over the last couple of lectures. So, we started with the concept of distributed plasticity, then we looked at the formulation for displacement or stiffness based element, and then the force or flexibility based element. Then we have studied numerical integration technique, and then we have looked at examples. First, we looked at linear elastic behavior, then strain hardening response, and also we have looked at elastic perfectly plastic response. And we have identified the limitations of displacement based as well as force based elements. So, let us recall that if you want to use a displacement based elements, whenever a member is undergoing inelastic deformation typically at the ends of beam elements, okay, where the bending moments are maximum. So, if you want to use displacement based elements, you have to discretize that portion into many small elements, right, because the assumption of displacement based formulation is that the curvature varies linearly, okay, and the axial strain remains constant along the length of the element. On the other hand, in force based element, we are not making any such assumption, and the equilibrium is enforced strictly, okay. So, we have seen that using one force based element, you can capture the nonlinear response of a member, okay. But if you use elastic perfectly plastic material response, then we have seen that there is a problem of localization at the section level. The peak curvature demand that we have seen in the previous example was actually dependent on the number of integration points, okay. Whereas in the global level, global force displacement response, we could get an objective solution, meaning that by changing the integration parameter, we saw that the global response was converging. But local response, for example, the peak curvature at a cross section was non-objective, okay. It was function of the number of integration points. So, today what we will do, we will look at strain softening response, where this problem will be even more serious, as we will discuss, okay. And then we will study one method to overcome this problem, and there are other methods also available in the literature, but in the interest of time, we will just talk about one method, which is called plastic hinge integration method, okay. So, with that, let us get started. So, we will first talk about the strain softening response, okay. So, let us say I have a reinforced concrete column. Now, if you recall from the previous lecture, the strain softening response is observed typically in reinforced concrete column subjected to high gravity load, okay. So, therefore, I am saying let us take a reinforced concrete cantilever column, which is subjected to some constant axial force, and then we are applying some lateral force. So, we can do it just by applying displacement and measure the force, okay. So, as you know, this is statically determinate structure, okay. So, there is no load in between meaning that within the element there is no other load, only at this node there is a load in the horizontal and vertical directions, okay. So, the bending moment diagram will vary linearly as shown, right. This is the moment distribution, okay. If you look at the curvature, so this is the height and this is the curvature, right. So, when you keep pushing it, so at some point there will be inelasticity developed at the base of the cantilever column, okay. So, the curvature variation is, let us say, something like that, okay, and we are talking about the actual behavior of this cantilever, right. Now, if you look at this cross section at the base and do a moment curvature analysis, let us say the moment curvature response looks something like that. So, it attains a peak and then the response reduces, okay. So, this is called strain softening response, as we discussed earlier. So, this is my moment axis and this is my curvature axis, okay. Now, let us say this is subjected to the constant gravity load and you start pushing the cantilever, okay. So, if you do so, then at the base what will happen? Well, the bending moment will keep on increasing and eventually reach the peak value, okay. So, I am calling this cross section number 1, okay, identified like that, and let us say here I take another section 2, 3, 4 and 5, right. So, these are 5 cross sections, physical cross sections that we are talking about, right. Now, the moment it attains the peak, accordingly the bending moment at 2 to 5 will be like this value, this value, this value, and here it is 0, right. So, let us say here is 2, 3, 4 and 5 on the moment rotation response, okay, because let us say the cross section is identical, along the height of the cantilever. So, this moment at point 2 is here 3, 4 and 5 on the moment versus curvature diagram, right. So, I am showing it on the same diagram because let us say the cross section is the same along the length of the cantilever. So, you have the same moment curvature response. It is just that cross section 1 has, let us say, attained the peak, 2 is here, 3, 4 and 5 is here. Okay. Now, if you keep pushing the cantilever, so what will happen? Eventually, the cross section at the base will go past the peak value. So, when it goes like this, what is happening? The bending moment is reducing in magnitude, right. So, that means if you look at this cross section, the bending moment was initially here at the peak, has now reduced to this value, right. So, what should happen to all other cross sections? So, 2 to 5, what should happen? Well, this should reduce, that means unload elastically so as to satisfy the equilibrium. What is my equilibrium? That my bending moment diagram has to be linear, right. That is a fact, because no matter whether you have inelastic deformation or not, the bending moment diagram must be a linear diagram. Okay. We are not talking about any geometric nonlinearity here. Okay. So, that means when this bending moment reduces at section 1 going like that, then the section 2 will unload elastically, right. So, that means the section 2 bending moment reduces to here. Section 3 will also unload elastically. This moment will go like that, and similarly 4 and 5 is sitting right here, because 5 is at the top where the bending moment is 0, right. So, now what is happening to the curvature? So, as you can see, from 5 to 2, all these sections are unloading elastically. That means their curvature will reduce. So, for example, here it will reduce to this, from here it will reduce to this, and here it will reduce to that, right. So, this is my new curvature distribution up to that point, right. Now, what is happening at this cross section? Well, we are going in this direction, right. So, the curvature is increasing. So, that means we are going like that. Okay. So, now if you keep pushing it further, so what will happen to your curvature diagram? I will draw it one more. So, it is going to go like that, like so, okay, right. So, this will keep on reducing because it will be unloading elastically, and at the base the curvature is going to increase, right. It will keep on increasing at the bottom cross section. So, we are moving along this direction, whereas all other sections will keep on unloading elastically. So, what is happening, that you have a curvature distribution which is pretty much linear up to this point, and then it increases significantly. Okay. So, that is what I stated here. Now, if you use a displacement based element, it is very difficult to capture this behavior, because in a displacement based element, within the element curvature varies linearly. So, from here to here you can use, let us say, one displacement based element, but then here you will need many displacement based elements to be able to capture this, which is like unrealistic. Okay. So, therefore, I am saying DBEs or displacement based elements fail to trace the real behavior of member because of assumption of linear curvature distribution. Okay. And because the assumed curvature distribution deviates significantly from the actual distribution during the element softening. So, therefore, it is very difficult. You have to use many displacement based elements. On the other hand, if we use a force based element, a single element will do the job, because we are not making any assumption related to the curvature distribution. We are just enforcing the equilibrium strictly. That means the bending moment varying linearly. Okay. So, that means the force based elements are better than the displacement based elements, right. But force based elements are also not free from issues. For example, let us take this concrete column. So, this is the cross section, it is a bridge PR. Okay. So, the cross section dimension is 550 by 550. There are 12 bars of 20 mm diameter. So, this equal sign is not very clear. The clear cover is 40 millimeter, right, and this column was considered and tested experimentally by Tanaka and Park in 1990. This is specimen number 7 in their study. So, this column is subjected to a gravity load of 0.3 Fc prime Ag, where Fc prime is the characteristic cylinder strength of concrete. So, you can say 30% of the gross section capacity was the axial force, right. And then they have applied lateral displacement to this column, and they have obtained the result base shear versus displacement. Base shear means this V or this V, and the displacement U, okay, under cyclic loading. So, this dashed line is the experimental data, right. I have taken this from the paper by Scott and Fenwick, which is listed at the end of this lecture slide, okay. So, what they have done, they have tried to simulate this response under monotonic loading, not the cyclic, monotonic loading, okay, and modeled this cross section using fiber section discretization, where the concrete was modeled using Mander model. You can go to the paper and see the different parameters that they have used, okay. But what I want to focus on is that they have used one force based element, okay. So, one FBE, right, and then they have changed the number of integration points that they considered along the length of the element, and they considered Gauss-Radau because it has an integration point at the end, okay. So, they have considered Gauss-Radau integration number of integration point 4, 5 and 6. Now, let us look at the result. So, base shear versus displacement result is something like this for NP is equal to 4, number of integration point is equal to 4. When it is 5, the result is going like that. When it is 6, the result is like that. So, what is happening? We see that the response depends on the integration points. Now, I do not know how many integration points needs to be used, right. So, that means the response is becoming non-objective, or we are losing the objectivity. In other words, the response is becoming subjective. It is depending on the number of integration points that we use. So, what is the exact solution? We do not know. But before we get into further discussion, let us understand why is this happening, why there is a loss of objectivity in the global response, okay. So, before we proceed further, let us make note of these few points. So, computed response is not objective because rate of unloading varies greatly as the number of integration points increases. That means, actually I should not say unloading, but it is like the post peak response that varies greatly as the number of integration point increases, okay. For softening section behavior, what happens? The deformation localizes at a single integration point, and this is what I want to elaborate further. We have seen in the previous lecture, if you consider elastic perfectly plastic material, we saw that the peak curvature demand was different when you keep using different number of integration points, right. So, the same thing is happening here, but we will discuss again in detail. So, unique solution does not exist. Computed response depends on characteristic length, that means basically the integration point weight, okay, integration weights of the quadrature. In this case, they used Gauss-Radau, okay. So, what is going on? Let us try to understand, okay. So, let us say I draw the same cantilever here, okay, and let us say this is my section moment curvature response, okay. So, I am writing this moment divided by length, so that I can call this the horizontal load H, because H times L is my bending moment here, right. So, let us say this is the moment versus curvature response of the base section, and it is the same for all other section, because it is the same concrete and same reinforcement going all throughout the element, okay. Now, let us say you have applied some displacement delta 1. So, this is my lateral force versus lateral displacement. So, at this displacement, let us say the lateral force is H3 when I am using 3 Gauss-Radau integration points, okay. So, here I am showing this is the cantilever, here is integration point 1, 2 and 3. when I am using 3 integration points, these are the weights that I am showing schematically. This is weight for this bottom integration, and for this one, this is the weight. For this one, this is the weight. Okay. So, for number of integration point equal to 3, let us say this is the solution and the load is H3, okay, at some displacement delta 1. Okay. And on the moment curvature response, we are just, we just went past the peak moment value, right. And the bending moment diagram is like this. So, this is my M3, okay, and the curvature is this one phi3, right. Okay. You are with me now. So, this is one solution. Now, what I am doing? I am saying instead of using 3 integration points, let us use 4 integration points. Okay. So, NP is equal to 4. So, my integration points are located, one is here. For Gauss-Radau, always you have integration points at the element ends. Okay. So, you have one here, and in between these are the 2 integration points. You can find out the location and the weights if you go back to my lecture on the numerical integration. But here I am showing schematically. So, for this integration point, the weight is now this much, whereas for 3, the weight was that much, right. Now, note that in the physical space, the sum of the weight of integration points is equal to the length of the element. Okay. So, what is happening when I have increased from NP equal to 3 to 4, this weight has reduced. Now, if you consider, let us say NP is equal to 5, number of integration points is equal to 5, then this is even further reduced, the weight of that section. Okay. Now, what we are doing when I apply this displacement, okay, so I am calculating the element deformation. So, basically this will go like so. So, let us say this is the center line. So, it goes like that, okay, and this is your delta. Now, you consider this to be in a simply supported basic system and determine from the chord what are your displacement or element and deformation. From there, you calculate, if it is displacement based, you calculate the section deformation, but in force based, we do not do that. We use an iterative algorithm. Okay. But eventually, what we satisfy the compatibility is this equation. What is this? The element in deformation vector, which is basically delta. So, this delta is axial. Okay. This is not the same delta as I am showing there. So, this is axial theta I and theta j, right. So, this is my V vector, which is equal to the integration 0 to L B transpose x V bar x dx. Now, what is V bar x? V bar x is my section deformation vector, epsilon x and psi x, right, axial strain and the curvature. So, now as I increase this V, how it is increased? By pushing it more to the right. Okay. So, then what is happening? We have already seen that there will be unloading here the moment we have crossed the peak. Okay. So, all other sections will unload elastically, that we have already seen. Now, here what we are doing? We are considering more and more number of integration points. So, what is happening? That the weight of the integration point is reducing as I increase the number of integration points. So, let me rewrite this using summation. So, L by 2 summation I is equal to 1 to number of integration point, and Wi is the weight for each integration points. Okay. B I transpose psi I. So, x is transformed to psi, where x varies from 0 to L and psi varies from -1 to +1. Okay. So, that is the mapping. Okay. And then this is the deformation vector. So, now notice here, if this quantity reduces, this has to increase for this to remain constant. Okay. So, that means if I apply delta 1 displacement to the tip of the cantilever, okay, and if I increase the number of integration point from 3 to 4, 4 to 5, then my weight is reducing as I am showing here. So, my curvature has to increase, okay, to be able to get the same answer. So, that means when I use NP is equal to 4, I will be here somewhere in the moment curvature response at the base of the cantilever. So, at this point, so this curvature is higher than the case when I am using 3 integration point. So, now corresponding to this curvature and this moment, where are we on the global force displacement response? We are here. This moment must be or this lateral force must be smaller than the previous case, because we have increased the curvature, which is a consequence of the reduction in the integration point weight, right. Similarly, for this case we have gone to the right further. So, this is phi 5, okay, and this force has reduced further, okay. So, if you keep on increasing the number of integration points, you see that this is dropping, much earlier. It will go up to the peak and then drop at a faster rate if you keep on increasing the number of integration points. So, the takeaway is that the deformation is getting localized, or the curvature is getting localized, which is what I am showing here. So, the black is for the case of 3 integration point, the red is for 4, and the blue is for 5. You can see that phi 3 is smaller than phi 4 is smaller than phi 5. Okay, and accordingly the bending moment diagram is also changing, and we are losing the objectivity in the global response. Losing objectivity meaning that it is becoming dependent on the number of integration points. So, this is what is happening. When the moment curvature response was elastic, perfectly plastic, then what happened? The global response was not affected because we are going in like that. Okay, so this was not affected previously. Only the peak curvature was affected, but when you have a softening response, then both section as well as global response will be losing the objectivity. Okay. Now, how do we handle this? So, there are various approaches in the literature. What we will discuss is called plastic hinge integration methods for force based elements. So, this was proposed by Scott and Fenwick. Okay. What is the idea? So, the idea is that we want to specify a plastic hinge length in the integration technique. So, meaning that if I go back, I will say that I have this column. So, this much portion is going to be my plastic hinge. And how do I get that? Well, there are empirical equations that people have developed. For example, Polly and Priestley in 1992 in their book, so they have given this equation for the plastic hinge length for a reinforced concrete member. What it is? LP is equal to 0.08 L plus 0.022 dB times Fy, where L is the length of the member in meter, dB is the diameter of longitudinal reinforcement in meter, Fy is the yield strength of longitudinal reinforcement in MPa. So, as you can see, this is an empirical equation which gives me the length of plastic hinge. Okay. So, what we are trying to do is confine all that inelastic deformation that is happening within the plastic hinge. Okay. So, that is the whole idea. We want to confine everything within LP. Now, how do we do that? Okay. So, the idea of this plastic hinge integration is we want to sample the section forces at element ends. Sample means we want to consider a cross section at the element ends, right, because that is where you have maximum bending moment. So, we will be using Gauss-Radau, that is what this point is saying, or something else. Gauss-Radau will not work, similar to Gauss-Radau where we have integration points at the element ends, right. Then we need to integrate quadratic polynomials exactly to provide exact solution for linear curvature distributions. So, what we mean by that, if you recall from our previous lecture, that the flexibility matrix for a force based element is integration 0 to L B transpose x F bar x B x dx, right. Now, what is this B? Well, the B is a matrix containing linear force interpolation function, which is exact because I know how bending moment varies if there is no element load. If there is element load, of course, I know how it varies, right. So, when there is no element load, B has linear polynomial, and then we are doing B transpose B here. Within that, I have the section flexibility matrix. Okay. So, this product becomes quadratic. So, for linear elastic behavior, I should be able to get exact solution. So, this is the second criteria. We should be able to integrate quadratic polynomials exactly to provide exact solution for linear curvature distributions. Okay. The third is integrate deformation over specified lengths. So, let us say at element end I, the length of plastic hinge is LPI, at end J, the plastic hinge length is LPJ, using a single section in each plastic hinge region, so that there is no question of changing the number of integration point and thereby reducing the weight. We will use in the plastic hinge region only one integration point. So, that is the whole idea. So, using this technique, I want to now come up with another integration scheme, that is what Scott and Fenwick proposed in 2006. So, you can go ahead and take a look at this paper. So, let me discuss the idea. So, we talked about Gauss-Legendry, we talked about Gauss-Lobato. There is another scheme called Gauss-Radau integration technique. So, if you recall, Gauss-Legendry is accurate for polynomials of degree up to 2n minus 1. Gauss-Radau is 2n minus 2 and Gauss-Lobato is 2n minus 3, right. So, we are talking about Gauss-Radau. For example, if you take two integration points, then 2 to the 4 minus 2 is 2. That means, by taking only two Gauss-Radau integration points, I can get exact solution for linear elastic behavior for force based elements, because as I showed, this is the product is quadratic. Okay. So, I will be able to get the exact solution. Now, let us look at the location of the integration points. When I take the element length minus 1 to plus 1, so let us say this is minus 1 and this is plus 1, my psi is starting at the center, this is 0, then the location is one integration point is here, that is the green I am showing here using the green color, and then the other integration point is at a distance 1 by 3, which is this, and there is no integration point at the other end. So, you have integration point only at one end of the element, the other end does not have any integration point. So, for example, look at this 3-point Gauss-Radau, you have at minus 1, then minus 0.29, then 0.69, okay, and these are the weights, right. And again, recall that the summation of weight is equal to 2, because it is equal to the length of the element in this normalized space minus 1 to plus 1. So, element length is equal to 2. Okay. Now, if you convert this to physical space, right, using this conversion. So, I am saying in this space I am using a variable psi bar, which is starting from this point instead of the center, and it is going from 0 to the length of the element, then psi bar and psi are related like this. Psi bar is equal to L by 2 times 1 plus psi. Okay. So, that means if you substitute 1 by 3 here, then this location becomes 2L by 3, and the weight is basically in this case for the physical space, the weight is WL by 2, okay, where W is the weight for this case. Okay. So, this weight now becomes 3L by 4, this weight which was 1 by 2 becomes L by 4. You just add the two weights, what do you get? You get the length of the element. So, in this case it is L, in this case it is 2. So, this is a way of normalizing and doing it easily. Okay. In OpenSys, if you ask for the location of integration points, okay, it will give you the location in this physical space. That means you will get one at 0 and 2L by 3 for the Gauss-Radau integration technique. Okay. Now, with that, let us say this is your element, okay, in the simply supported basic or deformation system, right. And we are saying that this part is my plastic hinge. This part is my plastic hinge, which I am getting the hinge length from empirical equations. Let us say this length I am calling LPI and this length I am calling LPJ. This is element end I, this is element end J, right. So, now if I use a 2-point Gauss-Radau, which is exact for linear behavior, okay. So, my first integration point is at 0, right. The second integration point is at 2 LPI by 3, where I am treating from here to here is my element length. Okay. So, if I take only this much length and treat it as the entire element and use the 2-point Gauss-Radau, so one integration point is here, the other integration point is there, and the weights are, this is LPI by 4, then this is 3 LPI by 4. How do I get that? Exactly this one, L by 4 and 3 L by 4. So, this L is actually I am saying within this range I am using Gauss-Radau, 2-point Gauss-Radau. But the problem is this entire plastic hinge now has 2 integration points. Our objective is to have only one integration point within the plastic hinge. So what they have suggested, so they have modified this Gauss-Radau, basically modified in the sense how you apply it. So instead of applying 2-point Gauss-Radau over a length of LPI, what if I apply this 2-point Gauss-Radau over a length of 4 LPI. So 4 times the length of plastic hinge. Then what happens? Well, this weight was LPI by 4. Now that weight will become LPI. So that means this integration point will have a weight which is equal to the length of the plastic hinge. The next integration point will have a weight. Earlier this weight was 3 LPI by 4. So that will now become 3 LPI, just a factor of 4, because here the total length was LP and here the total length is 4 times that. Okay. So at the left end you use Gauss-Radau over a length of 4 LPI. At the right end you do the same thing, again Gauss-Radau over a length of 4 LPJ, where LPJ is the length of the plastic hinge. Okay. So that is the idea. So now your integration point has a weight is equal to that which is given by empirical equation. Okay. So with this, what they have done, they have used 2 approaches for calculating the length of plastic hinge. One is the Pauli-Priestley equation and the other one is another equation. You can go to the paper and look at it, and their response is now matching quite well with the experimental data for base shear versus displacement. And at the section level, the moment curvature response is like that, okay, for the 2 cases of length of plastic hinge, right. And this is obtained using another approach which is called a regularization technique. In the interest of time, I will not be going through this. Okay. So the computed response accurately represents the experimental envelope, okay, and objectivity is maintained for the section level response. In other words, there is no change of integration points, hence there is no change of the section response. But the accuracy of this depends on how accurate is your length of plastic hinge. Okay. So in one of my studies, I have used this. Now note that the interior portion of this element, so if I go back, so here this portion of the element need not be linear elastic. So initially they said it can be linear elastic, but if you have gravity load or for some other load, let us say if there could be nonlinearity within the middle portion, then you can actually go ahead and use a Gauss-Legendry integration in the middle. Okay. So this is how they have implemented this in OpenSees, where at the 2 ends you have Gauss-Radau, in the middle you have Gauss-Legendry. So in this figure I have given you the weights for the end integration points. So this is Gauss-Radau, and then from here to here you have Gauss-Legendry, okay, and again on the right hand side you have Gauss-Radau. Okay. And this I am showing you a typical discretization of the cross section, where we are using confined for the core, unconfined for the cover, and these are the steel fibers. Okay. So with that, let us summarize what we have done. So we have discussed strain softening response and how it can actually give you problem. In other words, for strain softening response, if you use force based element, okay, whether it is a Gauss-Lobato or Gauss-Legendry, typically we use Gauss-Lobato because we have integration points at the element ends. Okay. So your section response as well as the global response can depend on the number of integration points you use, right, and we do not know how many integration points should be used, right. So that means the response, whether it is local or global, becomes non-objective. That means it loses objectivity. Okay. So that is where there are different techniques available in the literature. So what I have discussed here is called the plastic hinge based integration technique. So it is basically the same force beam column element. Okay. Only thing is that instead of using Gauss-Lobato, we are using Gauss-Radau at the 2 ends of the elements over a length of 4 times the plastic hinge length, where the plastic hinge length is an user defined input which comes from empirical equations. Okay. So that is how you can address this shortcoming of the force based element. Okay. So in the next topic we will now move on to geometric nonlinearity. So far we have discussed about material nonlinearity, how we model them. Now, the next we will consider geometric nonlinearity, and we will spend some 5-6 lectures on that, and then we will move on to nonlinear static and nonlinear dynamic analysis. Okay. So, these are the references that I have used in this lecture. Please go ahead and take a look if you are interested. With that, thank you and see you in the next lecture.